Now we want to start talking about the periodic table. And so the periodic table is where we can see all the information about, we contain all the information about all the different elements, right? And so we've seen this before, we've used it before, and now we want to talk a little bit about some of the kind of features and specificities. And we want to start with the idea of why is it called periodic? What does that mean? And why does it have this particular kind of weird shape? You know, with all these different kind of areas and colorations and things like that. So the idea of periodicity, this periodic, is the idea that if you take all of the elements and you arrange them by atomic number, you start to find some trends that show up, some trends in repetition of the physical and chemical properties. So here we can see 1, 2, 3, 4 all the way counting up. We can see first off that we have, say, at 2 is helium, unreactive gas, 10 is neon, unreactive gas, and 18 is argon, an unreactive gas. So we can see that all of those are shifted by 8. Similarly, 3, 11, 19 are all soft reactive metals. And so we can see there are properties that are repeating themselves, and they repeat themselves over what's called a period. A period is a length of time that separates basically some sort of repetition. Each period is one time through the pattern, if you will. So unreactive gas followed by soft reactive metal, you kind of follow that pattern. You get another unreactive gas, another soft reactive metal, and you continue through that pattern. So we know that's what periodic means. If we return to the overall orientation of the table, we can see that we have, say, 1 right here, 2, 3, 4, and we can see it counts up like this. So we're counting up left to right, and then we go top to bottom is how those atomic numbers are arranged in our periodic table as we go up and up. And so this particular arrangement of atoms in this way follows that idea of periodic. It follows those repeating patterns of chemical and physical properties. So when we look at the overall arrangement of all atoms, it would look something like this. You'll note that this 57 to 71, normally this is set aside on the bottom just to make the table a manageable size, but we really would have this overall representation of increasing, left to right and top to bottom to get that full orientation of the atomic numbers. So for each element, there's going to be a variety of information on our periodic table. We'll see here that each square usually has atomic number, chemical symbol, and element name, as well as that average atomic mass. Sometimes name and symbol aren't both used. So like you might only see Fe instead of iron. But generally, we're always going to want to use periodic tables. So I'll provide periodic tables. There's a variety that'll show up in the notes that you can use. If you find your own periodic table that you prefer, I would just encourage it to be one that has symbol and name. You're definitely always going to have number, symbol, and mass on there. It's just a matter of including that name. Because again, you don't need to memorize that iron is Fe. You will, but you don't need to specifically do flashcards or any sort of memorization along those lines. There's a lot of additional data that can be included on elements based on things like formatting. So the colors of the background or the letters or other different kind of fancy ways. So you can find a lot of fancy periodic tables with a lot of other information in there, some of which we want to talk about here. So the first designation that we see a lot of times for coloring is background color to denote those elements that are metals and those that are non-metals. And it's important when we talk about this idea of metals versus non-metals, we're talking about the elemental form. So for example, iron, we can see Fe right here. It is red, so that is a metal as an element. And so that would mean if you have pure iron, that is going to be a metal. But importantly, iron in a compound is not necessarily going to be a metal. You can form iron mixing with oxygen makes rust, which is not a metal, but iron by itself is a metal. And so we can see if we look at the periodic table overall, these colorations, the red in this case are metals and the yellow is non-metals. And we can see there's kind of a stark line that basically the left side of the periodic table, most of the periodic table, and to the left is metals. And then that right edge is where we find the non-metals. And so one of the things we can start to see is that this kind of seemingly random this seemingly kind of random orientation of atoms or elements is not random, right? By following this order based on atomic number, we can see that these patterns are the properties are changing based off those predictable patterns. That you have metals, 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 and then eventually their non-metals all show up. And then you kind of are following that pattern. So again, this is not a random shape, a random arrangement of the different elements. They are arranged in such a way that these properties vary in a predictable and periodic way. So what are the metals and nonmetals? Well, metals is most elements. Here, all the metals are highlighted. Metals are defined in general by the fact that they are malleable, they are shiny, and they are good conductors of electricity. Most elements in their pure elemental form are in fact metals. So you're going to be familiar with the properties of metals, not just elemental metals. These are properties that are generic. Metals are malleable. That means you can bend them. So if you think of like a coat hanger is a bended piece of metal. Malleable means you can work it and change its shape. And it can maintain the properties, chemical properties, but it has a new shape. So for example, aluminum, you can make it into aluminum foil. You can have aluminum cans. You can have aluminum in like a car body, in like a bigger, thicker piece, these different shapes. And that's really important and useful for metals. Glass is not a metal, and glass is not malleable. If you try to bend glass, it just breaks. So malleability is really important and useful for metals. Shiny metals reflect, kind of that sort of shimmer or reflection. You can see, kind of clearly the reflection on this piece of potassium over here, or especially on the platinum that we have right here. And finally, they're good conductors of electricity and heat. This is really important. This is a very distinguishing characteristic. There's copper wires in your house because they are carrying electricity through the house. It's important to note metals don't have to be solid. Mercury is a liquid metal. That's kind of the ultimate level of malleability. You can make a liquid into any shape you want. It won't hold that shape, but you can make a liquid into any shape you want. That is what malleability means. You can change the shape and it doesn't break. There are so many metals that we have different names for the different regions or types of metals that we have. One of the things you'll note is this language of main group. The high parts, or the periodic table on the two ends, generally we call those the main group of the periodic table. It's because that's where a lot of, you would say, the important elements show up. A lot of the elements that we use in chemistry a lot show up on those two sides, so they're kind of the main elements. And then we have this transition metals in between, and the transition metals, that name transition is because they are transitioning between the two parts of the main group. And so the transition metals have there's a lot of things down there that we use a lot of: iron, nickel, cobalt, copper, silver, gold. Those are all in the transition metals. And then we have these inner transition metals, because again, they're slotting in right there because they are inside the transition metals. More commonly, you hear them referred to as the rare earth metals. You'll note this is the other two, main group and transition. Those names are references to the shape of the periodic table. Rare earth is a reference to the fact that they are not common. They are not common on the Earth. So there's not a lot of these in and around the Earth. In the Earth, I don't know how to say around, but in when you're digging them out of the ground, there's not a ton of them. They're hard to find. So the nonmetals are then kind of everything else. So on the periodic table, they're going to be on the far right. Hydrogen also is a nonmetal, and that's actually on the far left. That's kind of an outlier, but hydrogen is a nonmetal. And the definition of nonmetals, if we think about their name is really just defined in opposition. They're just not metals. And so there's no real unifying properties. They're just not malleable, they are not shiny, and they're not good conductors of electricity. So they don't have any of the properties of metals. There's a lot of important elements that show up in the nonmetals. Carbon, nitrogen, oxygen, hydrogen are the main elements that make up living things. Phosphorus and sulfur making up kind of the rest of it. That's basically what all living things are made of, with a sprinkle of basically everything else. if we look at what their appearance, there's a lot of distinct properties. You could have something like carbon that has its diamond as pure carbon that is, see-through. It has that it's clear. It reflects light. It's not shining. That's reflecting light. You can also have carbon as graphite, where it's black powder. You can have yellow solid sulfurous, which is very crumbly. It's not malleable. It crumbles. You have liquid bromine, right? You can have liquids now that are dark, that in this case are red. There's a lot of variety in the properties of nonmetals because there's nothing unifying them. They're defined by being not something. When we look at the nonmetals, we can also see here that there's a lot of different phases of matter. Any element that is a gas at room temperature has to be a nonmetal. Because gases have to be nonmetals. And so you can see on this periodic table, blue font, blue letters correspond to gases, red correspond to liquids, and black correspond to solid. That's pretty common to use the colors of the letters. Black is most commonly solid. Red and blue, sometimes it depends on the particular periodic table whether or not they are liquid or gas. So you always want to be mindful of what it is. Blue is not always liquid. Oftentimes blue is liquid. Or blue is not always gas. Oftentimes blue is liquid and red is gas. But it kind of goes back and forth. You just want to be mindful of whatever the periodic table is that you're using. Black is almost always solid. And it's one of those things you don't need to memorize it because you can always find it on the periodic table. Do you also want to mention the idea of metalloids? So metalloids are the middle ground between metals and nonmetals. We talk about this definition as kind of a binary idea. Something's either a metal or a nonmetal, but really there is kind of a variation in these properties, right? There's this pattern, this period, this trend. And so these are the elements that are kind of on the border where they have a mix of properties. And so this name metalloid, that suffix oid means it looks like it is, but it's not. So metalloid means it looks like a metal, but it's not quite there. So factoid is commonly misused. Factoid as a word is something that looks like a fact, but it's false, right? It's a falsehood that's presented as fact. So metalloids, they look like metals, but they're not quite there. So their properties are, they're kind of, you can see here's examples of them all. They're all kind of shiny-ish. They're maybe a little bit malleable to an extent. And then they conduct electricity, kind of. A lot of metalloids are really important. For example, you'll recognize silicon. The fact that it is a metalloid is why we use it in computer processors. It conducts electricity, kind of. So it doesn't just freely conduct electricity, but you can get it to conduct electricity if you try. And so that's how you can control it. You can control that flow of electricity to work a computer. And so you could that's why we use silicon for it. Its metalloid properties are really, really important in that context. But for our purposes, for right now, moving forward, we still want to classify each element as either metal or non-metal, because we're going to care about some chemical implications that come up that are really going to be distinct based off metal, non-metal. And so for that purposes, we're going to want to still classify these metalloids as one or the other. In order to make that distinction, we can look at the background color in our periodic table. So this background color denotes metal, non-metal. We can see there is a line. It is a zigzag line. Everything to the right of that line over here is our nonmetals and hydrogen. That's the only thing we got to remember because normally hydrogen is situated right here. But that's a nonmetal, and everything else then over here is going to be our metals. So we can use that solid black line. Oftentimes this staircase is shown on periodic tables. You can also remember it just is a staircase that starts at boron, aluminum. It just goes one down, one over, one down, one over. Oftentimes it's on periodic table though. We just want to recognize that it's there. I think the standard one that I'll give when you're doing test prep doesn't have it on there, but you can always write it in yourself. Or use your own periodic table, whatever you like. But we do want to be able to recognize what's a metal, what's